We're going to look at some periodic trends. The first one will be atomic size. Well, how do you define atomic size, right? You got the nucleus and you've got these electrons, these like standing wave things. How do you measure that? And it's too small to see, right? So there's different ways of defining atomic size. What's called the van der Waals radius, and you don't need to remember which of these is which. I'm just going to show you a little bit what the difference would be. Van der Waals radius, also called a non-bonding. So if you have an atomic solid like krypton, you can look at the distance between two nuclei, which is measurable, and say, well, the atom size is half of that. The radius of the atom is half of that. Or we can look at a bonding radius, also known as a covalent radius. Here, a bromine molecule where there's a bond, a covalent bond between the two bromine atoms. And so you can measure the distance between the radius and divide that by 2. Well, the covalent radius and the van der Waals radius are not going to be the same because there's interaction of the electrons when you have a covalent bond, and so it's going to be smaller. So what we're going to do is we're just going to look at kind of an average of those radii, and this is based on just measuring a bunch of elements and compounds, okay? So that's what we're referring to. We can approximate the bond length by looking at the sum of the atomic radii. It's not precise, but it's a good approximation. That works for covalent bonds, not ionic bonds. So what's the trend in atomic size? Well, this is kind of a crazy graph, isn't it? Here's the radius of an atom, atomic radius in picometers as a function of atomic number. So it's down here, and it jumps up and it comes down, and it jumps up and it comes down. And you're like, what kind of a trend is that? Well, let's look at it this way. These are the alkali metals: lithium, sodium, potassium, rubidium, and cesium. That's going down group 1A. As you go down that column, they get bigger. It's not a linear relationship, but they get bigger. We predict that cesium is larger than sodium, right? That also works if we look at the noble gases. Helium, neon, argon, krypton, xenon, they get bigger as you go down the period, right? So that pretty much makes sense. As you go across a period, this would be lithium across period 2, lithium going across to neon, we see that there's a general decrease in the atomic size. And that one doesn't really make so much sense, and I think I'm ahead of myself in the slides anyway. Let's go back to this. When we're going down a group, the highest occupied principal level is getting larger, right? Here we have electrons in n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. As we go out, those levels are getting larger, right? They're also getting closer to each other, but it really makes sense that cesium is larger. But the atomic radius decreases across a period. So here we've got part of the periodic table, and what's listed here is the atomic radius. So let's say we look at period 3, sodium, 186, 160, 143. It's getting smaller as we go across. That doesn't make sense intuitively, right? Because argon weighs more than sodium. You expect it to be bigger. Going down, it increases, and the mass increases. You're like, well, that makes sense. A heavier thing is bigger. Sure. This one doesn't make sense. So what's going on there? It has to do with the interactions between electrons, that shielding and penetration business, effective nuclear charge. So electrons are simultaneously attracted by the nucleus and repelled by each other. The outer electrons, the valence electrons, are shielded by the inner core electrons. And so those outer electrons don't experience the full strength of the nuclear charge. so they're not pulled in as tightly. So here we have lithium again, 3 electrons in its nucleus, and we have 2 core electrons. These are in the 1s2 orbital. And again, they're not particles zigging around, they're standing waves that are occupying this space. And then we have our valence electron, which is a standing wave that's larger in size, the 2s1. So these guys are coming between the nucleus and this electron. Like that person with the great body on the beach putting on a parka, right? Now you can't see them as well, so they're not as attractive. So we can approximate the effective nuclear charge by taking the charge on the nucleus and subtracting the number of core electrons. So effectively, this has an attraction of +1 from the nucleus, not +3. Does that make sense? So the effective nuclear charge is the actual charge on the nucleus minus the number of core electrons. Valence electrons have a really, really small contribution to shielding, and so we're going to ignore them. So let's answer this question. What are the effective nuclear charges of nitrogen and argon? So for nitrogen, we need to know how many how many protons are in the nucleus for nitrogen. What element number is it? It's 7. There's seven protons. That's the actual charge. How many of those are core electrons? Okay, well let's look at the electron configuration. Another way you can think of this is, well, how many valence electrons does it have? It's got 5. The other electrons are core electrons. So there's 2 core electrons. And we can see it by also looking at the electron configuration. So its effective nuclear charge is 7 minus 2, or plus 5. And then let's look at argon. So how many electrons does argon have? How many protons? 18. That's the charge on the nucleus. How many valence electrons does argon have? 8. So core electrons would be number of electrons minus the valence electrons. So that would be 18 minus 8 would give us 10. 10 core electrons. So this is 18 minus 10, and so that would be a charge of plus 8. You can also look at the electron configuration. Yeah. So these are the valence electrons, and these are the core electrons. 2 plus 2 plus 6 is 10. So we're subtracting 10. Any questions? So Coulomb's law tells us that the energy of attraction is equal to Q1 times Q2 divided by the radius. Well, the charge on the electron is always -1. But the charge on the nucleus that valence electron experiences is determined by the shielding, and so is best approximated as this effective nuclear charge. So a -1 times plus 8 is a larger, more negative number than -1 times 5. The valence electrons in argon are more attracted to the nucleus. Everybody okay with that? Sort of. So as we go down a column, the principal quantum number is increasing, which makes sense, the radius is increasing. Going across a period, what we have is that the effective nuclear charge increases as you go across the period, but N stays the same. Those valence electrons are in the same level as you go across a period. So originally they would roughly be the same distance, but as the effective nuclear charge increases, that increasing charge pulls them in a little closer. Does that make sense? Let's just look at lithium. We already did nitrogen, and let's do neon. So the effective nuclear charge for nitrogen, we decided was 7 minus 2, which is plus 5. What's the effective nuclear charge for lithium? How many electrons does it have? How many protons? It has 3. How many core electrons does it have? It's the number of boxes in the previous row. Or we can think, well, it has 1 valence electron, all the other electrons are core electrons. So it has 2 core electrons. So we subtract the core electrons, that is an effective nuclear charge of plus 1. How many protons does neon have? 10. And how many core electrons? 2. The number of core electrons is the same when you go across a period, because the electrons are being added into the same principal energy level. So the number of core electrons is not changing, but the charge on the nucleus is changing, right? Neon has 10 protons being shielded by 2 electrons. Lithium has 3 protons being shielded by 2 nucleus. Yeah, those guys. Anyway, so the effective nuclear charge is increasing. Higher charge pulls the electrons in closer. Does that make sense? Oh, what about those transition metals? Oh, they're squirrely. If we look at atoms in the same group, the columns, they're going to increase as you go down, just like the main group elements. But as you look at a period, a row of transition metals, there's not a very good trend. They're actually roughly the same size. And the difference is, here, your valence shell is Ns2. Those d electrons, which is what's making the difference as you go across the transition metals, those are not valence electrons. They are core electrons. So the effective nuclear charge is approximately the same. So if we look at, let's say, vanadium has 23 protons, and let's look at zinc with 30 protons. So vanadium has a charge of 23. And how many core electrons does it have? Well, the valence electrons are the 4s2s, right? So everything except those 2 are core electrons. So that means there's 21 core electrons. Yeah? So that would be an effective nuclear charge of plus 2. Zinc has 30 protons. How many core electrons? Well, this is easiest to look at by how many valence electrons? 2. How many core electrons then? The rest of them, 28. This is only an approximation of the effective nuclear charge, but it's going to be the same as you go across because you're adding a proton and you're adding a core electron, not a valence electron. Okay? So you're adding +1 to the charge, and you're also adding 1 to the thing you're subtracting from it, and so you're going to get the same number every time. So we don't see a real good trend or change in size for the transition metals. So this is a sort of question you should be able to answer for an exam. On the basis of periodic trends, choose the larger atom in each pair, if possible. The if possible suggests that not possible is an answer. Okay, so tin or iodine. So we have to find these guys. There's iodine and here's tin. So we look at how do these relate to each other in the periodic table. They are in the same period, right? The same row. Does atomic size get smaller or larger as we go across? It gets smaller. That's the one that does not make immediate sense, right? Going down, getting bigger makes sense. This one is the opposite. So if they get smaller as we go across, which is bigger, tin or iodine? Tin. You see how I did that? Let's do another one. Germanium or polonium. And to answer these, you don't need to know what the names of the elements are. You just need to find the symbols on the periodic table. Where'd you go, Poe? There's Poe. Well, these are in different groups and different rows. So we have two trends to think about. The trend going across is that polonium would be smaller because they get smaller as you go across. But the trend, oops, didn't mean to write on that. Trend going down, they get bigger, right? So that trend predicts that polonium would be larger. So this is one where the answer might be, can't tell. Now, what if you're forced? You have to pick one. You have to pick one. Well, the trend going down is bigger differences because you're actually adding to larger and larger energy levels, right? The trend going across is small. It's the charge pulling things in a little tighter. So if you've got a conflicting trends here, the going down is bigger would win. So if you have to choose, I would choose polonium. Any questions? Chromium or tungsten? Why is tungsten W? Because its actual name is wolfram. Wolfram. Where'd you go, Wolfie? Thank you. It was hiding from me. And chromium. Which one's bigger? The tungsten, the W. The W is bigger because it's lower. Size gets bigger as you go down and smaller as you go left to right. And what we're going to see is that there's several other periodic trends, and they're either going to be the same as size or the exact opposite of size. So the way I recommend keeping this straight in your head is try to understand how this size thing works, okay? and then we can make sense of the others in relation to this. So, on the exam over this material, before you look at the questions, you might want to draw some lines on the periodic table that I give you and write out the trends before you start thinking too hard, right?